So this video is a review of integration by substitution. Sometimes we call it U-Substitution. The idea here is that sometimes we have to integrate functions that aren't just sine of x, cosine of x, e to the x, 1 over x, etc. So this is just a quick screenshot of your formula booklet, the integral section. So you'll see you have x to a power, 1 over x, sine of x, cosine of x, e to the x. If you are trying to integrate anything that's not just one of these basic integrals, you're probably going to have to do integration by substitution. And the trick about integration by substitution is that it's not a formula like when we differentiate and we have product rule, quotient rule, chain rule. Integration by substitution is a strategy that can help us a lot. It doesn't help us with everything, but it's a strategy and not a formula, so you have to know how to implement the strategy. So the goal with integration by substitution is to think of it kind of like the reverse of the chain rule, where you are trying to find an inside function, so to say, that you are going to define as u. And the reason is you're trying to make this integral more simple so that you can integrate it, because we can't integrate it by what it looks like here. Often when you have an integral that's a fraction like this, unless it's just a constant, unless it's just a constant over x, just basic, you're going to have to do integration by substitution. And so whenever it is a fraction that's not just something over x, a good place to start is by setting u equal to the denominator. That is what we can often think about as our quote inside function. So I'm going to go ahead and set u to be 1 plus e to the x. And so my integral now becomes e to the x divided by u, because I defined u as 1 plus e to the x. So I substituted. And in order to integrate our new, substituted integral, we need to get everything in terms of the same variable. We don't want to have u's and x's. So since we replaced this with u, we want to try to get all of these x's to go away as well. And so the trick to get rid of the dx is to take what you define u to be and to differentiate it. So I'm going to find du dx. The derivative of 1 is just 0. The derivative of e to the x is e to the x. And the reason I'm doing this is because now I have this equation that relates du to dx. And so we're trying to get rid of the dx and replace it with du. So I'm going to do that by solving, multiplying both sides by dx, so that I can actually solve for dx. So if I divide both sides then by e to the x, I now get this equation, dx equals du over e to the x. And that was my goal, is to differentiate my u so that I have du dx. That's what gives me a formula that I can replace, that I can use to replace, and solve for dx so that I can get rid of it. Because now I'm going to make another substitution. And instead of dx, I'm going to replace it with what we found it to be, which is du over e to the x. And this helps us a lot because now when we're looking at it, we can see that we have u's and we still have some x's, but hopefully what you're noticing is that when we multiply straight across, e to the x du over u times e to the x, really what happens is these e to the x's cancel. And so that leaves 1 over u du. Now, when we look at this, we've now taken the original equation and we've been able to completely restructure it so that it looks exactly like one of these formulas over here. And we see that when you integrate 1 over x, or 1 over u, you just get ln of that u. And so my integral becomes ln of u plus c, and we can't just leave that as ln of u plus c. because our integral, once we've evaluated it, does need to end all in terms of x. So we're going to replace u with what we originally defined it to be, which is 1 plus e to the x. And so that is our integral evaluated. So that's one example where you have a fraction that's not just 1 over x to start. Let's look at another example, and if we take a look at this one, we have sine of 3x, cosine of 3x dx. That's the integral we're trying to evaluate. And this one looks different than the last one because it looks as if we have a product, and that's what often trips people up, is they're trying to think, oh, we have a product, we have to use product rule. Keep in mind, like I said at the beginning, product rule is for differentiation. For integration, there is no product rule, quotient rule, etc. There's just this strategy of U-substitution. And so we have to try to decide what we think is our inside function. And honestly, what we might start by saying is, oh, well, maybe our inside function is 3x. However, if we were to set u as 3x, we'd still have sine of u, cosine of u, and that's not something that's on this integral list. So that's not going to work. If we were to try it, it just wouldn't get us anywhere. We wouldn't be able to solve, so we would know to kind of reevaluate that idea. So if that's not going to work, the next thing I would try is trying to decide whether to make sine of 3x u or cosine of 3x to be u. And to be honest, I think both of them will work. So I'm just going to pick one, and if it doesn't work, there's no harm, because all we will do from there is just try the other one. So we know that that makes our integral u times cosine of 3x dx. And so I'm going to differentiate u. That's always my next step. And keep in mind here that I have, when I'm differentiating this, I have a function 3x inside the function sine, so I'm going to have to use chain rule, right? So if I were to do it off to the side, I could just go ahead and say, okay, well, if u is 3x and y is sine of u, then du dx is 3, dy du is cosine of u. So the chain rule says 3 cosine of u, which is 3 cosine of 3x. So we can bring that up here. You should get good enough at chain rule that you can do that pretty fast. You may not even need to do this whole part off to the side. Okay, so we have 3 cosine of 3x. That's the derivative of sine of 3x. And so my next job is to get dx by itself. So that means that I have to multiply the dx to the other side, and then divide both sides by the 3 cosine of 3x. And the reason that I did that, again, is so that I can take this dx and I can replace it with du over 3 cosine of 3x. Now again, this is good news. When we've done this all this work right now, we can see that we have cosine of 3x on the top being multiplied by du over 3 cosine of 3x. So those cosine of 3x's are going to cancel. And that leaves us with u times, the 3 is on the bottom, so that's 1 over 3, times du. And keep in mind that anytime you have a constant like this 1/3 that's being multiplied to our function entirely, we can just pull that on out so it's out of our way. So now we have 1/3 times the integral of u du. And so now that should look a lot cleaner. We're able to integrate u, which means we're going to add 1 to the denominator, or to the, to the power, so that becomes u squared, and then we're going to divide by 2, or multiply by 1/2. So that's the integral. Plus c, never forget that part. And so if we were to simplify that, it'd give us 1 over 6 u squared plus c. And that is our answer, but it's not complete because we have not replaced u with our original function right now. So sine of 3x is u. So that is what is being squared. And you can leave your answer like that, or the more proper notation is to make that sine squared of 3x, but I think IB would accept your answer either way. Okay, so here's a good example that looks awfully similar to part A of our first question, so I think you should give it a try, pause the screen, and then take a look and see if you did it right. So, in order to work this problem, like I said, generally when we're using substitution as our strategy, we're going to set the denominator to be u, which means my integral is going to become 2x over u times dx. I'm going to differentiate du dx in order to isolate the dx so that in my integral I can replace dx with du. Again, du just says that we're integrating in terms of u, and that's our whole goal, is to get all of this in terms of u, so it's a more simple equation. The nice thing is these two x's are going to cancel, so we get 1 over u du, and the integral of 1 over u is ln of u plus c. And again, we have to replace u with our original function. And so there is our integral. Okay, 2 more parts. Take a look at 3a. Careful, because we've been practicing integration by substitution, but this question isn't asking us to integrate, it's asking us to differentiate. So go ahead and think about that for a second. This is a good review, because when we look at f of x equals sine cubed of x, we have to recognize what is being cubed here. And the most common mistake is to think that the x is being cubed, but it's not. It's all of sine of x that is being cubed. That's why they write that cubed there, is to indicate it's on the entire sine of x, not just x. So that when we rewrite it like that, it should look a lot clearer to see that this is a function, sine of x, inside of another function, x cubed. And so if we have a function and a function and we're trying to differentiate, we're going to use the chain rule. So I'm going to write out that chain rule. dy du times du dx. And I'm going to have to define my u, and that inside now is a lot clearer. That inside is sine of x. And that leaves the original function as just u cubed. So du dx is cosine of x. dy du is 3u squared. So when we substitute in, we get f prime of x equals 3u squared times cosine of x. We have to replace our u. So 3 times sine of x squared times cosine of x. And that's our function, although the more correct notation would be sine squared of x, like that. Again, IB really likes to combine questions where maybe part A asks you to differentiate and part B asks you to use integration. The reason being that they like to test your knowledge on both, obviously, but the tricky thing about that for you is that it can be easy to get yourself turned around about what you're doing. So you have to read carefully that you're differentiating on this problem. Okay, so looking at part B, and just confirming for part A that, yes, all of our answers were integer form, so we have everything written correctly. Okay, so 3b says, let g of x equal the square root of 3 sine of x times cosine of x to the 1/2. and it gives us a restriction. Find the volume generated when the curve is revolved through 2 pi about the x-axis. So in order to set this one up, we are going to need to think back to finding the volume, volumes of revolution. It's rotated 2 pi, which means it's rotated a full circle. The equation for volumes of revolution is from A to B of pi y squared, because that comes from pi r squared, right, the area of a circle, because it's revolving, dx. And so in order to find the volume of revolution, we are going to do pi, and I'm going to pull that pi forward because that's a constant, times y, which is square root of 3 sine of x, times cosine of x to the 1/2 squared dx. And it says that it's from 0 to pi over 2. And so the first thing I'm going to do before I do anything else is simplify, because this is going to make this a lot cleaner. And also, we don't want to have, right now, we have a function in this other function. So we don't want to have to be doing so many U-substitutions. So let's just simplify, because this is all multiplication here. We can apply the squared to each one of these individually. So that's only true of multiplication and division. If it were addition and subtraction, we couldn't. But we can do that, so that becomes 0 to pi over 2. The square root of 3 squared is just 3. Sine of x squared is sine squared of x. And then cosine of x to the 1/2 squared is just cosine of x. And hopefully when you started this question, you were noticing that there was something familiar about it to the first one. Or if you didn't recognize that, you're recognizing it now. Look at this and look at this. It's the same, right? This has turned into a very similar set of problems. So they don't want you to have to reinvent the wheel by doing U-substitution here, although you could, you definitely could. But hopefully we're recognizing that if we're trying to go backwards, that's the reverse of differentiation. Well, this was the derivative of this. So going backwards, the integral of this should be sine cubed of x. And so we should be able to go ahead and just put that like that, sine cubed of x. The plus c doesn't really matter right now. I'll write it for now. And that's going to all be evaluated from 0 to pi over 2. Again, if this was the derivative of sine cubed of x, then when we integrate this, we should get sine cubed of x, because integration is just going backwards from differentiation. So the plus c's are going to cancel, right? Because when we plug in pi over 2 and then we plug in 0, we're going to have c minus c, so that part's less important. So when I plug this in, we get sine cubed of pi over 2 minus pi times sine cubed of 0. And when we look at that, sine of pi over 2, that's straight up here, so that's 1. So pi times 1 cubed. And then, oh, I think I just wrote something wrong here. This, sorry about that, should have been, oh yeah, no, of 0, that was right. And then sine of 0 is still 0, so minus pi times 0 cubed. So that just gives us pi times 1 cubed, which is pi. Now let's talk about how we would have taken this integral and done it by hand if we had wanted to evaluate this integral by U substitution. We could have set U to be sine of x, and here's how I know that U would have been sine of x. That is clearly the inside function here. Anytime you have some sine squared of x, sine cubed of x, cosine cubed of x, anytime you have a sine or a cosine or a tangent function to a power, that function is going to be your u. So that means du dx is going to be cosine of x, and if we were to solve, dx would be du over cosine of x. And so, when we go here, this would become 3 u squared cosine of x times du over cosine of x. Great news, the cosines cancel. So we get 3 u squared du. What is the integral of 3u squared? That's just u cubed plus c. And we knew u was sine of x, so that's sine cubed of x plus c. So we could have done that with U-substitution. That would have been very doable. I've seen questions like that on IB problems where they expect you to do this with U-substitution, but they were just trying to save you some time up here, and I can't pull it back up, but just at the beginning, if you could recognize the going forwards and going backwards aspect of differentiation and integration, it would have saved you a lot of time. All right. If you want some practice doing this integration by substitution, in our Cambridge book for Math SL, you're looking at chapter 15B for your integration by substitution problems. And then overall, just practicing integration along with all of your rules, that's the basic rules, that's all going to be in chapter 13.